Shamrock Tube, you really believe from a military perspective that the moon isn't the new high ground or otherwise valuable, militarily speaking? Yes, I really believe that the moon is not the ultimate military high ground, that there is essentially zero military value for the moon. And let's just talk about the possible things that you might want to do with it, right? So let's say you set up your missile system on the moon and now you want to rain fire down on planet Earth. Well, okay, you're going to be putting those missiles on the Earth, you're going to be putting those missiles on the moon, and then it's going to take like 3 days for those missiles to arrive at Earth. And so whoever your enemy is, they're going to be able to get on an airplane, go to your house, punch you in the face, go back home, have lunch, right? They've got lots of time. The scarier thing is that when a nation is going to try and fire nuclear weapons from another place on Earth, then you've got 45 minutes. So would you rather the results of your first strike occur in 45 minutes or in 3 days? They're also going to be incredibly obvious. You're going to be watching these missiles blip, blip, blip towards us for 3 days. And so whoever nation you're trying to rain fire down on from above is going to be able to literally scratch build a defense. Find a ragtag team of deep oil drillers, put them on a refurbished space shuttle, send them up to the missiles to disarm them as they're making their way down from the moon to the Earth. So yeah, I think we can safely rule that out. And if you want any kind of either kinetic damage from these missiles or nuclear weapons from these missiles, well, that's a violation of the Outer Space Treaty. And obviously in this sort of new situation that we live in, if you're going to attempt to violate an international treaty, that's a slap on the wrist. That is a attaboy problem, not a severe consequences from all the other nations that have ratified this accord. But still, you're not allowed to put nukes in space. You're not allowed to put them in orbit. You're not allowed to put them on the moon, not on Mars. So that is a violation. And so if you go and people watch you send these giant spacecraft up to the moon and they're watching you deploy these giant nuclear missile systems on the moon, again, they're going to walk over to your house and they're going to politely ask you to decease. They're going to politely ask you to desist. Also maybe decease. Anyway, so that's not a real advantage. Now, what about observation? What if you want to just stare down at the Earth from above? Well, you're 400,000 kilometers away from the Earth. Compare that to the incredibly powerful keyhole satellites that are the size of Hubble Space Telescopes plus that are in low Earth orbit. They are 300 kilometers, 400 kilometers above the surface of the Earth. They can see incredibly small details, while some kind of observation post on the moon won't be able to see things smaller than the Eiffel Tower. So, or bigger, or the pyramids, things like that. We can't see Apollo equipment on the moon with the largest telescopes on Earth. The largest telescopes on Earth couldn't see Apollo equipment on the Earth. So, the largest telescopes on the moon wouldn't be able to see Apollo equipment on Earth. So again, it's too far away. What else have you got? Communication systems. So, when nations talk about their military operations in space, and, now people are starting to think about the military operations in cislunar space, that they're not concerned about using that as a place to attack Earth. They're thinking about that as a sort of, how are we going to defend our assets that we have deployed at the moon for communications, for research, for whatever purposes we put them at the moon. We probably need to deploy military assets to keep those things safe. But once you're down on the surface of the moon, they're really, now you got to get out of a gravity well to be able to make your way down to the Earth. It is, and you've got to cancel out the moon's orbital velocity. So you've got to not only escape the moon's gravity well, you've got to cancel out that sideways momentum. And that is still a very expensive thing compared to a suborbital launch from Earth. So yeah, I genuinely believe that the moon is not the ultimate military high ground. It is a terrible place to try and set up a military establishment at all. What it is great for is to do research, to go do science, to go to the moon, to learn more about the moon, that you can dig into the regolith and you will have you could take a core sample of the last billion years of everything that's happened in our local environment. You can find out about supernovae, gamma ray bursts, maybe even crunching up Dyson spheres that we talked about in Space Bites. You can set up a giant radio telescope on the far side of the moon and then use that as a way to probe the very beginning of the cosmos, or search for exoplanets and their magnetospheres that are interacting, and give you some kind of sense of how many planets there are that are out there. So the moon is a wonderful scientific place for humanity to go, and an absolutely terrible place for humanity to try to send a military. Okay. All right. Hey, everyone. Thanks for joining me for this possibly penultimate episode of the live Q&A show that we do every Monday at 5 p.m. So this is the 22nd. I'm going to queue up another one for the 29th. Super Luigi, Fraser, you live? Yes, I'm live. And then we'll go on hiatus. But I've got big plans. So if you were like watching YouTube a couple of nights ago, I did a pop-up stream where I was starting to test out my new smart telescope system, and that was 2 days ago. The system that I've got today is vastly better than the one that I had set up 2 days ago, and so hopefully I'm going to do more and more of these tests. And my sort of dream test is I'm just going to let the telescope run all night. It's just going to go target, 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 and I'll just sleep, and it'll just go after targets all on its own. So and then I'll do some live streams, and then if the live streams work out really well, then I'll bring in guests and I'll let them control the telescope. So I've got big plans, and the underlying technology now is feeling really, really rock solid, which is great. I've only got another couple of weeks of all day bug fixing to get to this place where it's actually going to do what I want. But it's really exciting. Like the quality, like I now feel like I'm getting images off of this telescope system that is better than the C-Star. And it has a 70 millimeter telescope lens and a really nice color camera, and it has a really good mount. So it should be better than the C-Star because it's sort of bigger in every way. But I wasn't at that point, but now I'm there. Now the images are great. So, and then you'll be able to watch, and you'll be able to tell me what to do, and you'll be able to drive this. So that's exciting. So just that's the update. Now go ahead and put any questions that you might have for me about space, astronomy, whatever. And then I will get to answering. The show is 2 hours long, so you're locked in until 7 o'clock Pacific Standard Time, daylight time. Is there even daylight time anymore now that we've switched away from it? Are we locked forever on daylight time? Yeah. Anyway. Okay, so what else? Some ground rules, of course. I try to give emphasis to the people who've never had a question answered before. So if you've never done that, then I like your chances. I am a journalist, not a scientist. And so I'm unable to provide you opinions about various scientific matters. Although, you can usually jailbreak me to get me to provide you an opinion about various scientific matters. But, it's generally my default to not do so. And then the last thing is, there's going to be lots of reasons why I don't answer your question. So don't take it personally. It might be that I've had that question recently, or I don't know the answer, or it's going to take a lot of math. I don't have time to do the math, or whatever. So, but I try to get through as many of these questions as I can. So hopefully this will be fun for all of us. Okay. All right. Let's see what questions we got. Unlimited Mind. Can you send us a good telescope model under $200 US dollars? Please. Can I send you a telescope? Are you asking me if I can send everybody who watches this channel a $200 telescope? No. I don't have that kind of money. But if you're wanting suggestions on how to get a telescope that is sort of under the $200 price, There are some options, but you're probably looking at used at this point. Well, the first thing that I would always recommend is that you go binoculars. If you get a pair of good astronomical binoculars, like a pair of Celestron Skymasters, they're in the $100 range, and they are like two telescopes that you put to your eyeballs. They are both, they are 15 by 70s. So you've got two, like my telescope is a 70 millimeter lens telescope. With a Celestron Skymaster, you've got two 70 millimeter telescopes side by side. And so the 15 is the magnification power, the 70 is the size of the aperture, the size of the glass on the other side of the binoculars. And 15s by 70s are quite amazing. Or 15 by 75s. Yeah, just amazing. You see a huge chunk of the sky. You can see the Milky Way. You can see star clusters. You can see the star clusters in Hercules. You can see nebulae. You can see the planets. You can look and see the rings on Saturn. The moon looks amazing. So there's a lot that you can do with a pair of binoculars. So if you've only got $200, that's my recommendation. Get a good pair of astronomical binoculars. And there are many people that's where they stop, that a good pair of astronomical binoculars is the beginning and the end of their journey into picking up astronomy gear. And then if you actually do want a telescope, you want to be able to look with sort of higher magnification at the planets or the moon, and you feel like you've got good enough dark sky that you can go and see stuff, then your best bet is Facebook. Look on Facebook Marketplace, and you will absolutely be able to get a telescope for under $200. Now you have to be careful because a lot of people will buy really crappy telescopes and then put them on Facebook. And the ones that you really want to avoid are the ones that look like kind of your classic, what we used to call the department store telescope. So it has this really long, spindly mount, and then it has this really long kind of refractor, like a lens telescope. Usually the eyepiece is sort of at an angle, and it's blue in my imagination. And, we always call those crappy department store telescopes. Those will only drive you crazy forever. But you'll see people posting, Celestron telescopes. I think it's like an EZ scope or EQ scope. Like 130 millimeter telescope. So it'll be like a 4-inch telescope. It'll be on a pretty good little squat mount. And then often it'll be on what's called a equatorial mount. So it'll allow you to tilt against the plane of the ecliptic of the Earth, and you can turn a little knob and the telescope will track objects that are in the night sky. The other thing that you want to keep your eyes peeled for is a Dobsonian telescope. And so often people will sell, say, a 4-inch Dobsonian telescope. Now, I bought an 8-inch Dobsonian telescope off of Facebook Marketplace, and I paid 500 Canadian, which is, I guess, like 400 US. And it is a monster. It is like the best telescope I've ever used for observing. You can get those kinds of deals all day, every day on Facebook Marketplace. So I would recommend that you go to Facebook, just watch it every day, see as telescopes are popping up. And my guess is you should be able to get a good telescope or a pair of binoculars in the $100 range. Good luck. Okay. Slowboy fuel pump. What is the best place in the United States for stargazing? I mean, in general, this is the general advice for what are the best places to go stargazing, is that you want a place that has very dry air, a place that does not have a lot of moisture in the atmosphere. And so in the United States, the best places are in the Southwest. So think like Arizona, New Mexico, Utah, Nevada, that kind of thing. And you also want a place that is very far away from light pollution. So once you get, I don't know, like to the Mississippi and then to the east, all of the, light pollution is impossible to escape from. But once you go out into the west, then you can be really far away from various city centers and get truly dark skies. There's this scale called the Bortle scale, and you can sort of seek the darkest skies using this Bortle scale. And then the last thing that you want is some kind of altitude. The higher up you can get, the less of the atmosphere is above you and the more of it that is below you. And so if you can go up a mountain in the southwest of the United States, in a place that is very far away from the city, you will have the most pristine skies possible. And in fact, there are a lot of observatories in the Southwest. There's a lot of them around, the Tucson area. And you can often go up to those observatories in the summertime, and you can set up your own telescope and you can take advantage of the really dark skies that they have up there as well. And of course, the other place that is incredible is Hawaii. Not so much when you are close to the water, but you've got these giant mountains on the Big Island of Hawaii and on Maui that you can go up to the top of these mountains or get pretty high up and then set up your telescope, and the seeing is the best in the world. The largest observatories in the world are set up on the Big Island of Hawaii for a good reason, because it is a great place to go. So the Southwest in the United States or Hawaii. B. Michael Neal. If von Neumann probes had independent AI, would they be von Neumann probes? What I'm asking is the movie Batteries Not Included about von Neumann probes? So it's been a long time since I've watched the movie Batteries Not Included, and I'm kind of afraid to do so because I'm sure it doesn't hold up. But if I remember, some kid finds some robots from space and repairs them, and then they become buddies. That's the movie. That's the gist of the movie. And so almost those are von Neumann probes, except they should have a better ability to repair and recover from whatever disaster befell them. So you would want your probes to be able to go to another star system, not run out of batteries, and instead find all of the local resources and start to duplicate themselves. But the AI side of it, I think, is very interesting because, one of the, like when we have life here on Earth, you can sort of imagine all life as little von Neumann probes, right? Bacteria goes, harvests the things that it needs from the environment around it, and then turns that into more copies of itself, and then those copies go to other places, and they make more copies of themselves. Like we've seen this game before. Mice are von Neumann probes. They go to your house, they eat a bunch of stuff, they make a bunch of babies, those babies go to other places, and so the world is covered in mice. And so it's that same idea. But the things that happen on Earth with life are the kinds of things that if someone was trying to design von Neumann probes, these self-replicating robot probes, they would have to account for that as well, which is that if there is no way to correct or get any kind of redundancy in the genetic code or resiliency, then you get these dead ends and life forms will peter out. And so, we have evolution has come up with all of these ideas, sexual, mating, where you sort of mix your genetic code with another entity. And so then the offspring is the mix of that. You have various ways to prevent cancers from happening and so on, right? And so if you try to create a von Neumann probe where you are programming it and you've given very specific, strict instructions on what to do, and then a cosmic ray hits it and knocks out a chunk of its memory that says, when you've built 10, go to sleep, and then that part is gone. And so it's just like, never go to sleep, just build as many as you can. And you can imagine over time, these von Neumann probes, their errors will build up over time. And so probably any civilization that is serious about having their self-replicating robot probes go across the cosmos, they're going to need to put some kind of intelligence level into the machine itself so that it can detect the presence of possible errors, flaws, deal with new situations in a way that makes a lot of sense, and then think about how it's going to add more redundancy when it makes a copy of itself. So, whenever I sort of think about this idea of unknown probes, I always think about the book, We Are Legion, I Am Bob, where, spoiler alert, guy gets turned into a von Neumann probe and then has to help save the Earth. And deals with a lot of the kinds of issues that you would sort of imagine. How do you make more copies of yourself? Are the copies different than you? Why are they different than you? How do you prevent yourself from how do you prevent this decay and so on? So it is a huge challenge. And, obviously we ever got to the point where we really could make self-replicating robot probes, then this is one of the issues. How do we prevent their decay, their inevitable genetic drift from all of the damage that they're going to take while they're out there? And then those copies will make copies and they will carry the bad code. And probably the solution is some level of intelligence, artificial intelligence. Jeff Hands, if you could choose what space telescope gets priority, what would you choose? Well, I would choose the space telescope that has priority, which is the Habitable Worlds Observatory. So back in 2020, the astronomical community got together and they made a bunch of recommendations to the the Science Foundation, to the various funding agencies, to NASA, and so on, and said, like, these are our priorities. These are the places inside the solar system, as well as the missions, the concepts that we want to understand. And there was a bunch of them. We want to see a mission to Enceladus. We want to see a sample return mission from Mars, and we would love to see a mission to Uranus or Neptune. And then on the astronomy, on the telescope side, they said we would like to have a telescope that has the resolution, the capability of directly observing Earth-sized worlds orbiting around sun-like stars. And there's a couple of previous ideas about this telescope. One was called LUVOIR, the Large Ultraviolet Infrared Telescope, and then the other one was called HABEX, which was an infrared telescope and have a free-floating starshade that would allow it to block the light from the stars so you could see the planets that were beside it. And then in the 2020 Decadal Survey, they decided to mash those ideas together. So they said, well, let's build something that is about the same size as James Webb, so about a 6.5 meter mirror, but let's also maybe have it fly with a starshade, and let's build a coronagraph on board that has the capability of blocking the light from the star, allowing you to see the exoplanets that are beside it. And that was the priority. And I am reading through the papers that are being released every day in the various journals, and I see papers pop up all the time where people are sort of still in the process of sort of calculating how good the coronagraph is going to have to be, how big will the starshade have to be, what is the capabilities, what are some options on how we can arrange the mirror. Do we make a primary, a regular mirror? Do we do an off-axis mirror? So there's like a bunch of these ideas, and that is the priority, and that is my priority. If I had to pick, that is the thing that I want the most, which is that, can you imagine how amazing it would be if we first just detected the Earth-sized world orbiting around a sun-like star within that star's habitable zone? That feels like it's a low bar. We know of 6,000 plus confirmed exoplanets. We know of 15,000 exoplanetary candidates, and yet we don't know of a single Earth-sized world orbiting around a sun-like star in that star's habitable zone. And so the Habitable Worlds Observatory will not only be able to find those worlds, it'll look at a star, keep watching it until it can rule out whether or not there are planets. And remember, all of the methods for finding planets used so far really depend on the orientation of the star and its planets. With the transit system, you want the planet to go in front of the star. With the radial velocity method, pretty much you want the planet to be going around the star. With the astrometry method, it's now you want it to be face on, and you want the planet to be going around the star face on. But with the direct observing, you just block the light from the star, and then wherever the planet is, you should be able to see it. And so Habitable Worlds Observatory should be able to just find those worlds. Like, oh, there's one at Alpha Centauri. Oh, there's one at, right? And so we'll suddenly know where all these planets are. And then the next question is going to be, can we study their atmospheres? And this telescope will do both. The telescope will find the planets, and then it will analyze the atmospheres of those planets to characterize them so we can understand, are they kind of similar to the Earth, right? Have they got large amounts of oxygen and nitrogen and carbon dioxide and methane and all these various trace gases? Are they totally different? Are they more like Venus? Do they have high amounts of carbon dioxide and nitrogen, but don't have the water vapor, and don't have whatever? So that is the dream, and that is sort of the next step for us trying to be able to understand and answer that question, right? That most important, what I consider to be the most important question that humanity has ever asked. Are we alone in the universe? We don't know the answer right now. And hopefully that telescope will give us that answer, or at least will move us towards an answer. I don't understand the question. There's a question from Cressholm. Oh, okay, I see the question there. Can I feature that? No, I can't. Okay. All right. Okay. I did it in the form of a question. Paul Michael Friedman, what is your favorite rocket or space vehicle? I do like the space shuttle. And I think that's probably just because I'm a generation of the space shuttle, that I was 10 years old when the space shuttle flew for the first time. Like, I watched the launch in 1981 of the first space shuttle, and it blew my mind. And I remember when there was the Challenger accident in 1986. I was on a paper route, and I was looking at the papers that I was delivering that day, and they were talking about the Challenger accident. And then I was a space journalist reporting on the 2003 loss of Columbia. And then I reported on dozens and dozens, more than 100 space shuttle missions. Because dozens, there was lots before I started reporting, but I started reporting in 1999 and through to 2011, and so I was able to report on space shuttle missions between that period. And right at 2011, I was able to take my father, and we went to the NASA, the Kennedy Space Center, to look at the space shuttle. And the plan was we were going to watch it launch, but it was delayed a month, so we didn't get a chance to watch it. But and I like the space shuttle. Like, I love the idea that you've got this reusable rocket plane that you can send cargo up to, and you can send astronauts, and the astronauts deploy the cargo, and they can repair things like the Hubble Space Telescope. The reality of the space shuttle is that it was dangerous, expensive. It was the wrong tool for the job, but it was the most well-built wrong tool I feel like humanity has ever done. That if you're given the challenge of building the wrong tool for the job, the engineers just made the most beautiful version of it. And the classic example of this are the engines, the RS-25 engines. These were like the Lamborghinis of rocket engines. These things were incredible. They were capable of producing more power than they had originally been designed for. They went through many flights. They kept getting reused. And in fact, when the space shuttle was retired, they took the RS-25 engines and they put them on the Space Launch System. And now the Space Launch System is crashing these beautiful RS-25, these pre-flown RS-25s into the ocean, which is very sad. But yeah, and so like just the legacy of the space shuttle. So for me, a vehicle capable of carrying humans into orbit looks like the space shuttle. And whenever I think about the space shuttle, I also think about the space shuttles that could have been. That when NASA started the development of the space shuttle back in the 1970s, even into the 1960s, right? Like they were working on the Apollo program. They knew they were going to be putting humans on the moon. And then at the same time, they were starting to think, well, what comes next? Well, what comes next is reusability. That it's incredibly expensive. We're crashing these rockets into the ocean. We should make a stack that is completely reusable. And if you go back to the original designs of the space shuttle, it looked like two space shuttles bolted onto each other. They both, one was like this giant carrier space shuttle, and then the other one was the actual orbiter, and the two were connected together. They would launch vertically, and then at a certain point they would detach, and the carrier had expended all of its fuel, and then it would fly back to the landing pad and land safely, while the space shuttle, the orbiter, would go up to orbit, and then it would carry out its mission, and then it would return. So it was a fully reusable two-stage rocket. It was essentially the same plan that SpaceX is trying to carry out with with Starship, and yet NASA engineers had worked on and had developed this back in the 1960s and 70s. And then there was a bunch of constraints and requirements that were put onto the space shuttle in terms of the payloads that it had to be able to do, some of the suppliers that they had to use. And so that idea of this fully reusable two-stage space shuttle was abandoned, and they went to the configuration that we see today. And we learned with the accidents that happened that it is just not a safe and stable arrangement. And you don't get the benefits of full reusability, which would make you be willing to take those kinds of risks. And now with advanced computers, now we're in this world where you've got the potential for a fully reusable two-stage rocket that returns to the launch pad and uses, cutting edge computers to be able to direct its location and be able to land it with pinpoint accuracy. That computer capability just didn't exist when the space shuttle was developed. But I just do love the space shuttle. It was a phenomenal machine, did some incredible science, and deserves a really important place in the history of human space exploration. A.B. Dwyer, regarding little red dots, could James Webb be focused to look for the closest youngest ones so we can learn something about their formation? Right, so little red dots, this is one of the big mysteries that James Webb revealed when it first went operational, that there were these objects that were on the scale of several light years across, maybe these were objects that were on the scale of tens of light years across, and yet they're seen early on at the beginning of the universe. They're putting out an enormous amount of energy, but that energy is in this red end of the spectrum. Like it seems to be very red light. And the traditional answer is that this should be a supermassive black hole. Like the only thing you get that has all those characteristics, something that is relatively small, producing an enormous amount of energy, that is an actively feeding supermassive black hole. But the thing that you get with black holes is X-ray radiation. They're so hot, they're producing so much energy that you see these higher wavelengths of radiation, and they just weren't seeing that with the little red dots. And now it appears the answer is yes, it is supermassive black holes. They're just enshrouded in this envelope of dust, that they are, consuming material so quickly that they're just puffing out dust like a fire, if you ever sat around a campfire where people are throwing wet wood on top of the campfire and just producing a lot of smoke, something like that. And so the question you're asking is, well, like, why do you have to look at the ones that are really far away? Why don't you just look at the ones that are really close and then help you understand them? But the problem is there are none that are close. That little red dots are seen at a time when the universe was less than 1 billion years old, 2 billion years old. And then, because the farther away you look out in space, the earlier you're looking backwards in time. That when you look at places that are older than that, you're looking at places that are 3 billion years old, 4 billion years old, you just don't see them anymore, that they're gone. People have wondered if they're transitioning into other objects that we do know of. Like, are these just turning into galaxies? But we just don't see examples of these relatively nearby. And so you just can't work it out, because all you've got is the ones that are seen early on in the age of the universe, when it's the hardest time to look back to because it's just so far away. Jimmy James, was that paper route a Times columnist? I had a few of those. It was the Vancouver Sun. So I had a paper route for the Vancouver Sun. And specifically I delivered in False Creek in Vancouver. D.O. What's your favorite naked eye or low magnitude observation? Man, doing astronomy with the unaided eye, with the naked eye, is tricky because there's not a lot that you can see compared to what you can see with a telescope. But what your eyes can see is a very wide field of view, which is a thing that your telescope can't see. And so I think the things that I like the best are when you have interesting conjunctions. So you've got like a crescent moon, and it's very close to Jupiter, and maybe Jupiter and Venus. And so you've got this almost smiley face up there in the sky. And that just looks great. And you can see that with the eyes, right? The other thing I really like is to be able to just see the Milky Way, where you've got this big wide view of the Milky Way from horizon to horizon. And you've got to be in like really dark skies to be able to see the Milky Way. But if the skies get dark enough, the Milky Way is just incredible. The other thing that I've seen once in my life is the Large and Small Magellanic Cloud. You can only see those from the southern hemisphere. So I was traveling in Australia, and I was able to see the Large and Small Magellanic Cloud. That was very cool. And then the one that is like dramatically better, that no camera or telescope can really capture, is the Northern Lights, the Aurora Borealis, the Southern Lights. That when you see pictures of the Northern Lights, you see these kind of really cool streaks in the sky. I think your thought is that this is something that is kind of very slow moving, that it's just this thing and you're taking this long exposure and you're getting these weird ripples in the sky. But it's nothing like that. It is alive. It is moving. You can see this sort of shimmer that goes across the sky and then goes the other way. And you can see it, and especially if it's happening like right above you, then you get these almost like snakes in the sky, and they're twisting and turning. And it just, watching video, seeing pictures of it, it just doesn't capture what it's like to watch this with your own eyes. And so that's the kind of stuff that I really like. I would say the other thing is meteor showers, that when you're outside and you're watching meteors go by, hopefully you've all seen a meteor in your life, but you see this point of light go across the sky, and you can see the trail of the meteor in the sky, and then you can watch it as it's like fades away. And the ones that are much brighter, they look better than the ones that are a lot fainter. And again, you just you can't capture that as a video. And so, there's stuff, comets, big comets. No, they look better in telescopes. Yeah, I'd say that's the kind of stuff that I enjoy doing just naked eye astronomy with. Paige Potter, will Artemis 4 visit Tranquility Base? No. So Tranquility Base, that was where the Apollo 11 astronauts landed on the moon. It's sort of like right there in the middle of the moon, facing the Earth. But the plan for the Artemis 4 mission is to go to the south pole of the moon. This is where the permanently shadowed craters are, where there should be deposits of water ice. So all of the Apollo missions landed in spots around the near side of the moon. Interesting geological places, but the place where the Artemis 4 mission is going to go is totally different than where all of the Apollo missions went. Clive Warren, when we finally get to the moon, what can we put on the moon that could be seen from Earth with the naked eye so we don't get a new conspiracy theory about not going to the moon? I think it's really important to say that there's literally nothing you could put on the moon that people wouldn't be able to come up with some kind of conspiracy theory about it. I mean, there are people who don't believe that the moon exists, that people don't believe that satellites exist. That you can go outside, you have an app that tells you when the International Space Station is going to fly overhead, and then you go outside at the right time, you look up, and boom, there it is. There is the International Space Station. If you have a powerful telescope, or even like a good pair of binoculars, you can look through them, and you can see the little TIE fighter shape of the space station as it's flying overhead. And the people with the best telescopes have taken images of the International Space Station and seen people doing spacewalks on the station, or various spacecraft that have recently docked with the station. And so no amount of evidence is going to convince people who, I guess, didn't use evidence to get to what they believe in the first place. But what could you put a laser on the moon, right? You put a really powerful light or a laser on the moon and you shine it towards the Earth. And if you make it powerful enough, I don't know the math, but it would have to be, very powerful. But there would be this light shining on the moon all the time. And it would be exactly where the moon base was, or right where the people landed on the moon. But, it'd be expensive and would require a lot of hardware setup and require battery systems to keep it going during the time when it's in the dark. It would be... you could probably put up something up there for a few $1 billion that would tell us that the humans landed on the moon. Or you could go the kind of the Chairface Chippendale route from the Tick, and you could just gouge out a big word on the moon. Maybe use nuclear weapons to bomb a big sign on the moon that says we landed here or something. But it's probably not worth the money. Janita, thoughts about the new papers about the center of the Milky Way not being a supermassive black hole, but instead some kind of fermionic matter? Yeah, we have reported on that quite a bit on Universe Today. I think I did a story about that on Space Bites. The gist is that, one explanation for the thing that is at the center of the Milky Way is a black hole, the standard, traditional, bog standard black hole, where you've got the singularity, you've got the event horizon that's around it, and then you've got the photon sphere and the accretion disk that's around that, and you are able to make observations of it with the Event Horizon Telescope. But this other idea is that, in fact, it's not a black hole, it is this sort of compressed area of another state of matter, this fermionic matter. And so it what looks like it has an event horizon is something that is very close to what a black hole has, but there are these little slight differences. And if I remember correctly, a better version of the Event Horizon Telescope should be able to make observations and be able to rule it out one way or the other. And it comes into that you'll have more of this, the area around the black hole where, a black hole, the event horizon is a really crisp line where inside nothing can escape it, outside things can escape it. And with the idea of a fermionic ball, that it's a little hazier around the center of the black hole. But it's still an enormous amount of material compressed down into a very tight space where it has immense gravity. Kenny Woodward, how long are we above, below, and in the galactic disk, and where we are, and how long before we enter the galactic disk? Are we in an arm, or can we catch up to an arm? Which one is moving faster? So we are in the galactic disk, and the galactic disk is pretty thick. Like, the galaxy is about 1,000 light years thick. It gets a little thicker when you are closer to the core of the galaxy, but where we are, it's it's a couple of thousand light years thick, and then it is 110,000 light years across. The Milky Way is definitely like a record, spinning record. But it's known that the stars in the Milky Way will oscillate. So it takes about 250 million years for the solar system to complete one orbit around the Milky Way. But that orbit also has an oscillation that carries it above and below the disk of the Milky Way. And that, I don't remember the exact rate that it happens, but we get like 2 aboves and 2 belows for each orbit that we take around the Milky Way. And so for most of the time, the solar system is embedded within the interstellar medium, and that is thought to be a potential source of protection from cosmic rays, because cosmic rays are coming at the solar system from the entire universe. They're coming from supernova, they're coming from supermassive black holes, they're coming from magnetars and pulsars, and they can be billions of light years away from us. And then these cosmic rays, essentially particles moving at almost the speed of light, can arrive with an enormous amount of energy and can break your DNA and cause all kinds of problems. And so one theory about the history of mass extinctions on Earth is that they're caused by the solar system rising above the plane of the Milky Way. And so if it does that, now you are no longer taking advantage of all of the combined heliospheres of all of the stars in the Milky Way. You are less protected, and then you can receive a higher dose of cosmic rays. And some astronomers think they've tied times when the solar system was higher or lower to times of mass extinctions in the past. And when you think about how long it takes for the sun to be able to go around the center of the Milky Way, 230 million years or whatever it is, the last time the sun was in this rough position, there were dinosaurs, and the time before that, dinosaurs hadn't even evolved yet. So it takes a long time for the sun to make this journey around, and this is something that is considered. I wouldn't say that it is mainstream, but people have produced papers on this idea. So we're in the Orion spur of the Sagittarius arm of the Milky Way. Ravi, good, better, best. Do you think mining helium-3 is the real reason for this new moon base race? No, absolutely not. Helium-3 is this sort of isotope of helium, and one of the, it's thought that the advantage of using helium-3 in your fusion reactors is that you get less dangerous radiation coming out of the reactor. And I forget the exact atomic explanation for this, but with normal hydrogen fusion or with normal helium fusion, you're going to get an excess of gamma radiation coming out of your reactor. But if you do this helium-3, then you get less of that gamma radiation. And so that would allow you to have a fusion reactor that is in a tighter space, closer to people, and you can worry about it less as causing radiation damage. And helium-3 is located here on Earth. I mean, it's in deposits of helium, which are part of, say, oil and gas reserves and things like that. But because helium-3 is being generated by the sun, this stuff is implanting on the surface of the moon, and then it has a much higher ratio of helium-3 in the regolith than what you might find down on Earth. And it's not nothing. It is definitely something, but the first step for where you would want to actually have your helium-3 is that you would want to be able to have a fusion power. And at this point in the technology curve of humanity, we do not have controllable fusion power. We have uncontrollable fusion power. We have thermonuclear weapons. We know how to harness the power of the sun to release megaton weapons, but we don't know how to do this in a controlled manner. And the classic joke is that the classic joke is that fusion power is always 30 years away. And we're at a point now where there is a huge facility that's being built in Europe called ITER. The Germans are working on their version of a fusion reactor. The Chinese are working on a bunch of fusion reactors. There's a bunch of startups in the United States that are working on fusion reactors. And I'm guessing that we're about 30 years away from fusion power. Which, like, what do you know? We're always still. And so think about it. And that's not just even hydrogen fusion. We'll probably start in deuterium fusion, which is going to be an easier form of fusion, then probably move to tritium fusion, and then move to proper hydrogen fusion, and then maybe move to helium-3 fusion, and then work out miniaturization. We are 50. Well, no, I mean, come on, honestly, fusion's 30 years out. Then helium fusion, like maybe 100 years out. So although when we get to a place where we do want to have helium fusion, we will be able to, then we'll be able to go to the moon and pick up some of this stuff. But that feels like a real long shot. And so no, the race for the moon base is to put a base on the moon. That there is, real, genuine scientific inquiry that can be done on the moon. It is a valuable place to go for science. You have just the geologic questions you have about the moon itself. You have the regolith and how the regolith serves as a time capsule for all of the events that have happened in our vicinity astronomically. And then you have the observations that you can make from the far side of the moon using radio telescopes. And both the Americans and the Chinese are trying to set up a base on the moon. And, part of it, of course, is to demonstrate your technological superiority. Like we can put a base on the moon. We are really good at what we do. But it's also just important to just say that all nations invest a certain amount of their production into scientific inquiry. And that there are scientific questions that can be answered by the moon. And so both the United States and Europe and Canada and Japan and the Chinese are doing science, and the moon is a platform to do that science. So no, it's crazy to me that people would, that we cannot plan very far into the future. We're just not that organized about that kind of stuff. And so I think, I always say, don't worry about people stealing your ideas. If your ideas are any good, you'll have to jam them down people's throats. That if we get to a place where helium-3 is finally viable, then maybe people are going to consider, should we harvest this from the moon? But even then, probably not. Jeff Hands, if your legs were another set of arms, would you live in microgravity? Should people have feet changed to hands if they live in low Earth orbit? So I don't want to live in low Earth orbit. I think it makes sense for us to eventually put, some kind of space stations in low Earth orbit long term. Once the International Space Station goes down, you got the Chinese space station. But microgravity is bad for the human body for long periods of time. Like you can do a year at most, and then after that point, you are starting to feel bad. You've lost bone mass, you've lost muscle mass. There's fluid redistribution. There's problems with your eyes, and then there's even other issues that we're not entirely sure about. So although the human body can survive in weightlessness for a year, maybe a little bit more than that, you really don't want to go longer than that. And so I can't imagine us ever thinking that we want to live in weightlessness for forever, for like that is our habitat, because you may have feet for hands or hands for feet, but and so you can climb around from place to place in weightlessness, but you're still experiencing the bone loss, the muscle loss, the fluid distribution, the problems with your eyes, and so on and so forth. And so really the solution, if humanity wants to live long-term in space, we've got to figure out how to create some kind of artificial gravity in space. We need some kind of rotating space station that we can be in, and then we would be able to cancel out the problem of the weightlessness. But then now you've gone and changed your feet into hands, and so now you can't walk around on this one gravity that you've got in the giant rotating space station. So you will regret it. So no, I don't think changing your to feet to hands just so you can do well on one mission to the International Space Station is the right play. But who knows? Like in the future, it might be really easy to change feet to hands. It might just be like a day operation, quick surgery. And it might be that that's the call that all the astronauts make, that they get ready to go to space to do their year on the International Space Station, and they all get their foot to hand surgery. And now they all have, and they, take a little time to do a little bit more physical therapy. So they're up to speed using their hand feet, and then off to space they go. And then when they come back to Earth, they put back, or they regrow their regular feet, and then they're back to operations. But even that, I think they would not, even if it was painless, safe, I don't think they'd want to do it. Silsib, being that the Earth contains so much iron in its core, would the sun explode if a planet such as Earth crashed directly into the sun? So the sun already contains dozens of times more iron than the Earth does. So if iron was poison to the sun, then the sun would have died a long time ago. And the thing is that iron is not poison to the sun. And I get this question a lot. And it comes from thinking through what happens when a star goes supernova. So think about, the most massive stars in the universe. They are fusing elements in their core. You've got hydrogen going into helium. You've got helium going into neon, carbon, or as helium goes into carbon, and then you've got oxygen, neon, and you're kind of moving your way up the periodic table of elements. And the sun stops when it gets to carbon and oxygen, and then it is no longer able to produce fusion in its core, and so it shuts down and cools down and turns into a white dwarf. But the more massive stars, they have more gravity. They can maintain the conditions of fusion longer in their cores, and so they go higher up the periodic table of elements. And when you do fusion, you extract energy as part of the process. So when you mash hydrogen together, you get helium and energy. And it's that energy that actually is maintaining the shape of the star. The radiation is pushing out the star that is counteracting the gravity that is pulling the star inward. And you get this thing called hydrostatic equilibrium. The shape of the star, the size of the star is radiation pressure outward, gravity inward. And those are in balance. But for the largest stars, you keep walking up the periodic table of elements, until you're finally turning things into iron. And when it comes to fusion, iron does not produce any radiation. And so it is the equivalent of we was talking about, it's the equivalent of ash. You can't light ash on fire. All of the parts that you were able to derive energy from are all gone. You're left with charcoal, right? You can't turn charcoal into fire. Well, I guess you can though, right? So, but anyway, it's the equivalent of ash, right? It's already burned. And so when a star reaches iron at its core, then it is no longer producing the photons the gamma ray photons from the fusion process. So now the force that was pushing outward, the the light pressure, can no longer counteract the gravity that is pulling it together. And so the star collapses, it implodes. And so you sort of talk about it in this idea that the moment iron starts being produced in the star dies. And so that people have said, whoa, so like iron is poison to stars. So how much iron, right? Well, the reality is iron is not poison to stars. And if you added iron to a star, it is the equivalent of you eating grass, right? You are deriving no nutrients, no carbohydrates, no energy from grass, but it's not going to kill you. You're just going to poop it out. And the sun is the same thing, which is that what the sun wants is it wants hydrogen to be able to run its fusion reactions and maintain its hydrostatic equilibrium. If you're going to put iron into the sun, that is just stuff that is not going to be part of the fusion process. It's going to be there, it's going to get in the way, but it is not going to be fusing and releasing energy. And so then the question is like, how much grass could you eat before you died? Right? And the amount is you would have to like fill your digestive tract with this stuff, right? You just be constantly eating grass and pooping it out, and you're not getting any food, and you would just get more and more malnutrition, and you would die. And the sun is the same thing. So you could just keep putting iron into the sun. It would be fine. It wouldn't care until the sun was all iron. And then it would no longer have hydrogen fuel, and so it would no longer be able to fusion, and it would die. So so iron is not poison to stars. Okay. Corey Kearney, quick question. Is this live only here? Is there a live podcast like thing? So we leave this live stream here up on the YouTube channel. So, do I get to put that up? Yeah. Okay. So we do this live stream every Monday, and we leave it up on the YouTube channel. So if you missed the live version of it, which you're in right now, then you can always just watch the shows after the fact. And we try to sort of make it clear that this is the new one and these are the old ones. And so there's like 1-2 hour live stream on my channel every single week. And we absolutely have a podcast. So if you don't want to listen to this thing live and you want to just listen to it after the fact and listen to it edited, so you get to lose all of the ums and ahs and all of my dad noises, then you can do that. So you just do a search for the Universe Today podcast and you will get the audio edition of everything that we do. Unlimited Mind. Would you consider to make a small question and answers in Switzerland and make us all happy in this great small country? Like, are you asking me to come to Switzerland and do a question show in Switzerland? Yeah, be great. I'd love to. Just somebody needs to pay for my flight and hotel and wants to organize the event. I'll come and give a talk at your, astronomical society. This happens occasionally. I've been summoned to various events around the world to participate in them. And I don't love to do it because, travel is very hard on the human body. And I already kind of travel quite a bit, but that happens from time to time. I think people always ask me like, oh, you should do like some kind of live show. You should do some kind of thing where you go put on events in various places. And, I know that the big, popular, super A1 YouTubers can do that. I took my kids to a Jacksepticeye live show in Seattle a couple of years ago, and it was a packed room and it was a good time. But we've tried to do live shows related to Astronomy Cast, and we have, I don't know how many listeners we have on Astronomy Cast every week, 100,000, 50,000. I don't know. I don't look at the numbers. And we have not been able to have people show up for our live events. So I really think that I could come to your town and we could have a beer. And if you want, you can ask me a bunch of space questions. But the sort of the idea of like, oh, it'd be really cool to do like a live show. It's just, I'm not famous enough. I don't have the draw to be able to make that worth anybody's time. And so instead, I show up here on the internet every week and try to entertain as many people as I can. Tom Holroyd. If one member of a binary pair went supernova and left a black hole behind, the other star would still orbit the hole. Yeah, absolutely. And this happens all the time. So you've got two stars, two massive stars that are orbiting around each other, or one massive star and then another star that's orbiting around that massive star. And then the massive star goes supernova. It leaves behind a black hole, and the star is still continuing to orbit the black hole. And it just depends on the distance from the star to the black hole, what happens next. If the star is really far away from the black hole, then nothing happens next. That star can continue orbiting around the black hole for billions of years in a completely stable manner. You know, people always imagine black holes as like the most powerful vacuum cleaners in the universe, that once you're near a black hole, you're going to get sucked in. But it's not like that at all. You could replace the sun with a black hole, and all the planets would perfectly orbit around the black hole sun for billions and billions of years. But if the star is closer to the black hole, or was closer to the massive star that then turned into the black hole, and the black hole is able to start drawing material off of this star, then things get weird. And so you're going to get this stream of material that is going from the star to the black hole. And in fact, the very first black hole that was ever discovered, Cygnus X1, was found because of this arrangement, that you've got this black hole, it's being orbited by a star, the star is supplying material to the black hole, that material is building up into an accretion disk around the black hole, giving off X-ray radiation that then telescopes on Earth or in space can detect the presence of this black hole. And so you're going to get this outer envelope of the star is being drawn away. And then as the star is sort of producing this cloud of material that's around it, maybe this causes friction. This might cause the star to get closer and closer to the black hole. And you can end up with the situation where the star eventually gets close enough to the black hole, gets torn apart. You may see some kind of, possibly a gamma ray burst or some really bright explosion as the star is finally being dismantled. But, because most massive stars in the universe are part of binary trinary systems. Like most big stars are in multiple star systems. And so that means that a lot of the cases, those massive stars are going to turn into black holes. Those black holes are going to be orbited by a star. And then there will be interactions between the star and the black hole into sort of the future of time. I answered this question before. Okay, let me just from Alpha. Whoops. Sun spells. All right, hold on a second. There's a number. Okay. All right. So let me get this question. Verstovsek. Is the sun loud? Could we hear it if there was air between the Earth and the sun? How loud would it be? So yes, the sun is incredibly loud. And the reason that we can't hear the sound come from the sun is because there is no medium to transmit the sound. If we could, if there was air between us and the sun would be 100 decibels. And 100 decibels is very loud. Let me see what Wolfram Alpha says about that. I'm trying to think. It's like a space shuttle. Oops. The space shuttle was 90 decibels. Okay, so 100 decibels is equivalent to a chainsaw going off beside you. So, so imagine, right? You're looking up into the sky and there's just the constant screaming sound, chainsaw level. Someone is running a chainsaw beside your ear, and that is the sound of the sun at all times. So fortunately, there is no medium between us and the sun that can transmit the sound that is coming from the sun, because that would be loud. Yeah. 100 decibels at 150,000. No, 150 million. So 100 decibels at 150 million kilometers away. Tim Pointing comments on the recent AFP story about the Earth maybe not getting swallowed by the red giant sun. Article talks about the growing sun having stronger gravity field. So I haven't read this specific article, but I have reported on all of the flip-flops between will the sun consume the Earth or will it not. So here's what's going to happen to the sun, right? The sun is a main sequence star. It is converting hydrogen into helium in its core, and as it goes through that process, it is slowly heating up a little bit. Eventually, it's going to run out of easily usable hydrogen in its core, and it's going to switch to helium burning. So it's now going to be converting helium into carbon and oxygen. And that process is like just a totally different temperature. And the outcome of that is that it causes the sun to expand. It's a much hotter process at the center of the sun that gives off more heat. That causes, this idea of the radiation pressure that's coming from the heat inside the sun, that causes the sun to expand outward. Now, it will be cooler on the outside of the sun, and so the sun will turn red, and it will be much, much bigger. And it's believed that the sun will consume Mercury and Venus. But then the question is, what'll it do to the Earth? We don't entirely know. One issue is that we don't know really just like how big the sun is going to get, but it'll be like really close, like kind of the size of the orbit of the Earth. But the other thing is that when the sun goes through this process of going through becoming a red giant star, it's actually it doesn't happen one time. The sun it's this cycle. So the sun starts burning up helium in the core. It expands outward because it's now putting out more heat at the center of the star. It lasts in this newer shape for millions of years, but then the core is starting to cool down because it no longer has all of this pressure pushing down at the core. This causes the core to cool down. The helium burning shuts off. The star compresses back down. The center heats up. The star expands outward again, and it's going to do this for about 1 billion years. And each time that it does this, it sheds a layer of material out into space. And when you look at, say, the really cool planetary nebulae, things like the Ring Nebula, the Helix Nebula, these are the results. This is what you see after a star is dying or has died, because it has puffed out these rings of material out into space. And, it's going to take about 1 billion years for the sun to go through these death throes until it's finally can no longer, just like nothing left to give. All that's left is the carbon center that remains. And that's why they talk about, eventually this will just be like a giant diamond, right? And so now the sun has lost half of its mass. So typically half of the mass in the sun is in its core. And so the orbits of the planets depend on the mass of the sun. And so as the sun loses mass, then the planets will will range outward. They will start to drift away from the sun to balance. No, wait, I might have this backwards. Make sure. As the sun loses mass, then they'll come closer. Yeah. But let's keep it ambiguous, because I don't want to sort of say it either way until I get it right. Or someone in the chat can fix me on this one. But as the sun loses mass, it's essentially mass. As the sun loses mass, then its gravity field will adapt, and that'll change the positions of the planets. And so often you'll get these papers where someone will say, "Oh, I've done the math. And when the sun goes into its red giant phase, it's going to eat Mercury, eat Venus." Nobody argues about that, right? Venus and Mercury, they're done for. And then but it won't quite eat the Earth. Instead, the Earth will be just like horribly scorched. All the oceans will be gone. It'll be utterly unlivable, but it won't be consumed. But I've heard other people say, no, it'll take out the Earth, and it'll also take out Mars. So when you think about Betelgeuse, like Betelgeuse extends out to the orbit of Jupiter. Now, Betelgeuse is a red supergiant. It has dozens of times the mass of the sun, but is going through a similar version of that process. So these red giants can get really, really big. And then other people will say, no, it's definitely going to, it's only going to eat Venus, and it's going to be lots of space. So to say, like, every year or so, somebody does the math, their results come out, and then if it's the opposite of the one that people are expecting, then there will be a short little media burst, and then it comes back the other way. Christian Desaillier, if the Earth gets 100 tons of meteorites a day, how much does the moon get, and how much of a problem is that for a future moon base? So I don't know the exact math of how much debris is raining down on the moon, but it's essentially a function of its surface area compared to the Earth's surface area. The Earth is bigger, therefore the Earth gets more. I don't know, let's say it's 20 tons a day. I don't know the exact number. But is that a problem for a future moon base? It's not no problem. But it's probably not a big problem. But the issue is that the moon doesn't have an atmosphere. And so on Earth, all of that 100 tons of debris that's raining down on planet Earth, and most of it is teeny tiny, right? It's mostly it's dust sized or sand sized, is it burns up in the atmosphere. And so we get a meteor. When that stuff gets to the moon, there is no atmosphere. So that stuff hits the ground, and you get this kind of pelting of these micrometeorites hitting the surface of the moon all the time. And there's this term for it. It's like lunar gardening, I think it's called, because essentially all of this debris is constantly raining down on the surface of the moon and kind of churning it up and mixing in that top layer of the moon. And most of it is going to be harmless, that you'll be out, you'll be standing in your moon base under the big dome on the moon. And every now and then you'll hear this little ping where a piece of space debris or a micrometeorite hit the dome and, didn't do enough damage to be able to go through it. But you just look at the surface of the moon, and that tells you all you need to know about what can happen. And so there are larger objects. And in fact, we are now observing them on a regular basis. When the Artemis 2 astronauts were doing their flyby around the far side of the moon, they were able to look on the dark portion of the moon, and they saw a flash from a micrometeorite impacting the surface of the moon. If there was a base under that place where the micrometeorite hit, or maybe it was a meteorite, like something bigger, then there would have been some damage, and we would have a hull breach, and there would be red lights going off, and people would be running around, and air would be swooshing out of the base, and that would be a bad day. And it's not a question of if, it's just a matter of when. If you leave that base on the surface of the moon for a long period of time, It's just a matter of time before that thing gets hit. So what is the solution? The solution is to go underground. The solution is that you build your lunar base in a lava tube. And again, you can see a lava tube. The lava tube formed 3 billion years ago. The surface of the tube has a hole, but it's not constant. It doesn't have holes across the entire thing. So if you build inside that lava tube, you're probably safe. But really all you got to do is put your base down and then bring a bulldozer and just dump regolith on top of it, and that will protect you from the kinds of objects that could hit your moon base. And then the other option is that you can put your base down in a chasm on the moon. So instead of being just out there on the highlands out in the shooting gallery, you find some place that's a deep crack, and then you put your base down at the bottom of that deep crack. And so it has to be a perfect angle for a meteorite to be able to, or it has to be a perfect angle for a meteoroid to hit your base and do any damage. And that's also a good protection from radiation, because cosmic rays are just like meteoroids, right? They are going from some out there distant location. They're just a particle, and they are moving at close to the speed of light. And so if you're out there on the surface of the moon, then you are going to experience hundreds of times as much radiation as we experience down on the surface of the Earth. But if you go down to the bottom of some chasm, imagine some box canyon in the southwest of the United States, then the cosmic rays have to have a direct hit straight down inside the canyon. And you can match up the radiation exposure that you would get being on the surface of the moon to what you would experience on Earth, as long as you found the right structure to put your base down at the bottom. So I think a good place to put a moon base would be some kind of box canyon with really steep sides on the surface of the moon. Of course, then, there could be a landslide that could drop rocks down on top. But, now we're just coming up with cool plot points for a future space movie set on the moon. Oh, there you go. Avipar says 0.07 the surface area of the Earth. So much less. Science compliance. Fraser, have you ever, or do you have any plans to grind your own telescope mirror? I have a giant list of things in my mind, of things that I would, projects that I would love to do. And one of those it'd be super cool to grind your own mirror. You really know what it's like to build your own telescope. That would be cool. And then we'll pop open an Instructables link and watch as people explain how they grind mirrors. And that sounds too hard. But it is definitely a thing that you can do, that you can buy glass blanks of the size of the mirror. You can buy, say, a 200 millimeter one, 205, which is the size of like an 8-inch mirror, but you can get much bigger ones. And then you buy the mirror surface shape that you use as a sort of a template to find out whether or not your mirror has the right shape. And then you just use sandpaper. And you have sanding blocks that sort of are curved and follow the shape of what the mirror is going to be. And then you just sit there and you sand and you sand and you sand and you grind, and you get this thing down to the shape that you want. And then you can send the mirror away, or the piece of glass away, and people will coat it in aluminum for you. And it brings the cost down significantly, that you can build your own telescope for tens of dollars that is of the same quality as a telescope that you might spend $1,000 from, because you've done all the work. You've ground the primary mirror. You've maybe bought the secondary mirror. You've got a tube. People use a thing called a sonotube, which is like this cardboard tube. People also make ones out of trusses. So, as long as you can keep the mirror and then have some kind of light block around the mirror, people have used stove tubes to be able to make their mirrors. So it is definitely a thing. And now I'm talking myself into it, right? I'm like, oh, that'd be super cool. That'd be a great project if I had an infinite amount of time. But then I think about the work that I'm doing to try and make this smart telescope work for me. And no, I'm still excited about it. So do I have plans? Yes, I have plans. Yeah, it sounds great. I want to do this. Squirrel. So yeah, I'll let you know when I take that on. Darren Green, whatever happened to the probe that touched the sun? I think you're talking about the Parker Solar Probe, which was a mission that was launched by NASA like a decade ago. And this spacecraft was going to get closer and closer and closer to the sun and capture images from a distance that we have never seen before. And whatever happened to it, it's still going. The Parker Solar Probe has made many orbits around the sun. It has done flybys of Venus and Mercury to tweak its orbit, allowing it to get even closer to the sun. And it's sort of reached its final place now. It's sort of run out of gravitational maneuvers to get any closer. But every few months, it makes another close flyby of the sun. It goes very, very fast around it. It heats up. It has this sort of heat shield in front of the spacecraft. It heats up, and it's going right through the outer atmosphere of the sun. And so it's experiencing the magnetic environment, the particles that are flowing away from the sun, all of the charges, and it's able to send that information back home to NASA, and then they're integrating that with the other observations that are being made of the sun. You have the European Solar Orbiter spacecraft, you have the Daniel K. Inouye solar telescope down on Earth, you have the Proba satellite from the European Space Agency. So you have the SOHO, you have there's all of these different spacecraft that are all observing the sun at the same time. And the Parker Solar Probe is the one that is getting extremely close. Let me just get the closest approach. I think it's like 3 million. So it's 6.1 million kilometers away from the surface of the sun. So the sun is like 1.5 million kilometers across, and the Parker Solar Probe gets within 6 million kilometers of the surface of the sun. And we are 150-ish million kilometers away from the sun. So that is super close. And the spacecraft was designed to handle that kind of heat, and it is continuing to send data home. It's not actually touching the sun, though. Kevin Jelezniaksky. Is it possible that radiation from a supernova or a burst of energy somewhere is traveling towards us right now and can destroy the Earth, or at least all life, or are we just too far away? Yes, it is possible that there is a burst of energy that is heading towards the Earth right now that could cause a mass extinction on planet Earth. So we've got to sort of think about the kinds of sources that could cause that kind of destruction. And the one that people think about is, say, a supernova, right? That if a star goes supernova and it is relatively close to us, then we will be doomed. But a supernova has to be really, really close. It has to be like 25 light years away from us. And there are no stars capable of going supernova within 25 light years of us. There are stars that are in the few hundred light years away from us that are capable of going supernova, but if they do, then the damage they would do is not meaningful, and so we don't have to worry about this. And the kind of damage that you're looking at is mainly that when the radiation arrives at Earth, it destroys the ozone layer and allows more radiation to get into the planet than it normally would, and then life on Earth dies because of increased amounts of radiation. That's the big risk that we face. So then there is another kind of explosion that is more dangerous than a supernova, and it's called a gamma ray burst. And that is, we're not still entirely sure what causes a gamma ray burst, but it seems to be a bigger version of a supernova, that you get a star that implodes, and it creates these collimated bursts of energy that come out the poles of the star. And if you happen to be staring right down the barrel of one of these beams, then it can cause that same kind of damage. And the good news is that there don't seem to be any of these stars that are relatively close to us, within, and this is the scary part, actually, it gets scarier, but, you could be within within the galaxy, that, something could be 25,000 light years away from us. It could fire one of these beams at us, and it could cause that mass extinction on Earth. But astronomers have looked out there for all the kinds of potential gamma ray bursts, and we don't, they don't see any stars that have the potential of blasting us with a gamma ray burst. There was a gamma ray burst that went off in another galaxy that was like it was like more than 10 light years away from us. There was a gamma ray burst that went off in a relatively nearby galaxy. It was more than 10 million light years away from us. It's like not just in the Milky Way, but in an entirely different galaxy. And we happened to be hit by the beam, and the entire Earth's atmosphere wobbled after this beam hit us from several million light years away. So it's certainly believed that mass extinctions in the past on Earth have been the result of this gamma ray burst striking the planet, but they are incredibly rare. We don't know of any stars that have the potential to do this that are close enough to cause damage to the planet. And so, but could there be one out there? Yeah. So there could be a star that exploded 10,000 years ago, 10,000 light years away from us, and it looks like a star to us today, but in fact it is a gamma ray burst, and the beam of energy is traveling towards us, and at some point that beam is going to wash past the Earth, and we would have a bad day. But astronomers haven't identified any stars that are potential for doing that. So I would, when I think about the kinds of risks that we face from space, we have to be more concerned about the star that is right there inside the solar system, right, with its potential for unleashing very powerful flares that will give, causes a very bad day, compared to a gamma ray burst. I really wouldn't worry about gamma ray bursts. And like the scariest possible things are fascinating, but they're very unlikely. Paige Potter, has studying the universe changed any of your personal philosophies or values? How? So I was raised in a secular household, right? Religion in Canada is not as big as it is in other nations. I knew people who were raised in a religious household. I was not. And so I've never experienced religion in a sort of like, I knew people who were some people were Jewish, some people were Christian, but I just was raised like you just exist. Here we are. Who knows what happens when you die? We don't go anywhere on Sundays. We just go to the park. But one of the things that you see in people of religious faith is this just kind of sense of wonder and appreciation of this larger scale, this larger universe that we find ourselves in. And, I think for people who are religious, they find themselves they're part of some plan, and that makes them feel good, right? That life isn't just this meaningless, pushing around your atoms in a hostile universe until you die, and then you never mattered, right? And so that religion gives people some level of comfort. And it was just like, I never understood it. I didn't understand that. Like, it doesn't make any sense to me. How do you know? What is your evidence that this is true? Like, would you rather believe things that you know to be true versus things that you hope are true? Isn't it better to kind of know what's real, and then you can sort of base your life on that thing that's real? But I think that we crave, as human beings, is just, the way we evolved under purely natural reasons, to crave this connection with the divine, to crave this connection with something that is bigger than us. And that, if you think that there is nothing that is bigger than us, or your sort of worldview, your model is that you just like, nothing has convinced you that it is a thing that is true, that is bigger than you. Well, there is something that is bigger than you, and that's the universe. And that when you think about the scale of the universe, both in terms of just the size of the universe and the age of the universe and the amount of stuff that's in the universe and all of the different combinations that could be out there in terms of stars and planets and stars, it's filled my spirit, my just sort of my existence with a sense of wonder and awe and enthusiasm and excitement. And in the same way that I had when I was like a 4-year-old. Like if you had known 4-year-old Fraser, you would have found him very annoying because he just never stopped asking questions and he never stopped talking. But he was just so curious and so effervescent. I don't know how to describe it. I was a lot, okay? I was a lot as a kid. And I think that as people get older, they lose that connection. They get ground down. Life shows up. You've got responsibilities. Life gets tough. And for me, being connected to this field, being connected to this kind of research, or just science in general, just makes me feel wonderful. And it gives me that connection that I think a lot of people lack. That they just don't have this chance to just go, whoa, right? That you want sometimes. So I would say that is the sort of like the biggest philosophical feeling. I don't think it's changed my values, right? Like I think I have, my values remain largely unchanged, but I think just contemplating the scale of the cosmos is something that allows you to be grounded and be humble about your place on Earth, in the family, in your relationships, in your family, of what you do here on this planet. And so I think that's been good for me. Unlimited Mind. I think Carl Sagan is the starter or Stephen Hawking. You know what I mean? I don't exactly know what you mean. Starter. So like, are you talking about like on hockey? Is like, are you going to start with, are you going to put Carl Sagan on the ice? Are you going to put Stephen Hawking on the ice first? Or is it like, who would you want to read first to help you understand the cosmos better? It's Carl Sagan all day, every day. Stephen Hawking is fascinating. I mean, he's got some great ideas and he came up with some incredible discoveries about black holes and other stuff. And, he's got his book, A Brief History of Time, but it's a thick read. It's a tough read. And like, maybe I would understand it much better now if I read A Brief History of Time, but I read it when I was 16. And so I don't think not a lot of it made sense to me, but Carl Sagan is so accessible. I mean, he was a scientist working in planetary science. He was working on missions, sending spacecraft, the Voyagers, the Viking missions, other tons and tons of science papers. And then he just did this incredible job of connecting the world to what was happening in space and astronomy. And you go back and you watch Cosmos, the original Cosmos show with him in 1982, 1983. And it still resonates. Like, it's still great. The bell bottoms and the wide lapels and the crappy graphics and some of the outdated understanding of the cosmos is a downside, but there are parts where he does just a wonderful job. And that's the least of it. Like I think, we've seen Carl Sagan on interviews and things like that, but where Carl Sagan was the GOAT is his writing, his books. So he did Cosmos, which was sort of what the TV series was based on, and sort of took you on this guided tour through the universe. It was great. He did Pale Blue Dot, which was one of the books that inspired me to start Universe Today. Like, I was reading Pale Blue Dot, talking about Earth and our place in the cosmos and what the future of humanity in space and the astronomical questions that we have. And I was, shook, right? And I was like, Oh, yeah, I must dedicate my life to space, Dr. Sagan. Um, and then even in science fiction, you read Contact and or watch the movie, but read Contact. It's great. It's a great science fiction story. But the most influential book written by Carl Sagan for me was Demon Haunted World: Science is a Candle in the Dark. And this is a book that he wrote about how important science is and how the scientific method is a way of us illuminating the dark, mysterious universe around us, and that there are many different ways that people have proposed to know things, to seek truth, be it philosophy, religion, but science is very different from these other methodologies. It is testable. It is inherently skeptical of its own methods. It relies on you being able to set up some kind of scientific apparatus, try to demonstrate some kind of result, and then walk away from that apparatus. Tell the other scientists to say, tear this apart. Show me why I'm wrong. I've got to be wrong. Help me find out why. That is not what a philosopher will say. A philosopher will try to convince you of their opinion. That is not what a religious person will say. A religious person will try to get you to believe in the same things that they believe. But a scientist will beg you to prove them wrong. Right? Totally different methodology. And really, science is obviously a flavor of philosophy, right? So it's not really accurate to say the philosophers aren't trying to do that. Some are, some aren't. But science is one offshoot of philosophy that focuses on this sort of skeptical, confrontational method of seeking out the truth about our nature or reality. And in Demon Haunted World, Carl Sagan deeply investigates the rise of pseudoscience. So he takes on homeopathy and UFOs and all of these bad ideas and shows how they aren't scientific. They don't provide the kind of rigorous debate, the kind of evidence that is required to be able to rise to a level of an actual scientific theory. And he is sort of preparing us for the kind of world that we find ourselves in today. Like, if Carl Sagan was alive, he could write a new edition to Demon Haunted World tomorrow, and it would be incredibly useful for humanity at this time where people disagree about all kinds of scientific questions, not because the underlying scientific questions are incorrect. It is because people are no longer agreeing on this common truth. It's, that let's trust in expertise. Let's investigate in certain ways. Let's perform scientific studies. Like, it has become this political juggernaut. And you talk to anybody who has some position on some various scientific questions. If I say global warming, right, there's going to be some people who are going to roll their eyes and they're going to talk about politics, right? When really it's a scientific question. And there's a methodology that you can go to get to the bottom of global warming, and you can come up to an answer. I talk about COVID. There is, it is a scientific question. Either there is a disease or there is not. Either the disease works a certain way or does not. Either the vaccine is effective or it's not. Either masks will work or they don't, right? These are all scientific questions. And that you have people that are making claims because you have an audience. You can go straight out to the internet and you can just broadcast whatever you want to say to an audience, and you can get people following you, whether or not you are actually showing the results of the things that you say. And the kinds of things that Carl Sagan was concerned about in Demon Haunted World are just like times 1,000 right now. So, yeah, Carl Sagan is the one that I'm putting on the ice first, because I really want to break the backs of whatever hockey team we're going to be going against. And Carl Sagan will just tear them apart. J-Dog, what other field of science or other topic do you wish there was a Fraser-Cain twin reporting on? There's got to be, there are people who are doing amazing work in every single field of science. I think one of the great things about science is there are a lot of science communicators who are, I sort of imagine us as remoras, those little fish that stick along beside sharks while the sharks are out there hunting. The remoras are picking up some of the scraps and helping out. Or maybe they're not helping out. Maybe they're just picking up the scraps. But anyway, I feel like my job as a science communicator is to help scientists communicate the work that they're doing to a wider audience. They're busy. They're doing the science. They shouldn't also be responsible to communicate the science. I mean, there are some who do an amazing job of it. And if they all did a good job of it, I would no longer have a job. But because they're busy and they're trying to do the science and they don't have time to try and communicate what they're doing, I will try to pick away at the bits and pieces of that I can. But there are incredible science communicators in so many fields. I mean, there's a ton of people doing great work on this sort of, the climate change conspiracies that are going on. Just to have a thing, Potholder 54, Simon Clark, you've got Michael Mann. So there's there's a ton of that. You've got sort of more general science communication and skepticism. Professor Dave Explains. You've got Anton Petrov, who will take on not just astronomy related stuff, but other topics. You've got Joe Scott is doing a great job of science communication. There are scientists who are still doing a lot of work in science communication, PBS Space Time with Matt O'Dowd, or you've got like David Kipping. And then you've got different fields, right? And I don't know them, right? Because I'm interested in the topics that I'm interested in, but I know that there are people who are doing great work in soil science and biology and virology and parasites and, all of these different concepts, geology, geography, all this stuff is happening across. So I wouldn't say that I'm, my guess is that there are science communicators that are doing as equal or a better job than me in pretty much every field that matters in science. The problem is that there is, for those of us who are trying to do our job communicating science, Hank Green and the whole empire of SciShow, I mean, they're doing a phenomenal job of communicating science. Anyway, so for every one of us that is attempting to actually try to properly communicate science, there is a vast empire of deep moneyed interests that are attempting to destroy people's faith in science or trust in science, understanding of science, because they have something to gain, right? If you are a company that earns hundreds of billions of dollars a year from producing a chemical, and the chemical is causing damage to the environment, then all you have to do is try to discredit the people who are studying the damage to the environment to then be able to continue producing your chemical and make your money, right? And so I think that unfortunately, and you see the sort of the final form. I don't know if we're at the final form yet, but we are at a very evolved form of sort of anti-science discourse in the world today over a lot of topics that are true, genuine scientific questions that have genuine implications for humanity, where money is being thrown at it to muddy the water and make people's lives more miserable. And that people will suffer the consequences down the road because people are spending that money today, in the way that the tobacco companies spent millions of dollars for decades to muddy the water over whether or not cigarette smoking was bad for your health. You are seeing that same kind of money times much, much more being spent trying to make people question whether or not certain scientific studies are accurate or not. And we will suffer the consequences down the road. And for some of you, you're going to nod your head. You're going to go, yeah, it sucks. I really wish there was more people that are out there trying to communicate the science, or I wish there was ways that we could stop that money from being spent to besmirch the name of the scientist. The reality is that scientists this is how they roll, right? Which is that if you're going to question their work, you got to put up or shut up. You got to deliver the scientific results. And so, so more science communicators would be great. More people more science education would be great across every single field. And yeah, I totally like, oh man, here's this field that I barely understand, but I really wish I could invest the time and become a good communicator in that field, understand the material top to bottom, and participate in the communicating of that science. I'm just one man. I can only work on one field. I feel grateful that I know as much about space and astronomy as I do, and I'm able to, I hope, participate in making the lives of the scientists a little bit easier, and allowing the people who actually do care about science, I'm able to give them something that they want. And the more people that are out there that can do it, the better. And there is a huge need. I mean, there is a huge need for better science communication. So if you feel like you've got that instinct at all, then I beg you to get in there and help participate in science communication. The problem is there's not a lot of money, right? The money does not come from science communication. You know, there's not giant flows of funding from NASA and so on to pay us to teach you about space and astronomy. There is no money coming from NASA, right? My money comes from the patrons. My money comes from advertising. But boy, is there money if you want to say the opposite. I mean, there's large flows of money out there if you want to cast doubt on science. So, yeah. JJ's Quest. Certain sciences are known for having better peer review efficacy and strenuousness than others. Where does astrophysics lie in that spectrum compared to the others, in your opinion? Yeah, I mean, I think, you know, when you think about a lot of the sciences like psychology, economics, behavioral things, there's kind of money to be made, and there's the duplication crisis. So people are having a hard time duplicating the results of various scientific papers. And that is a big problem. There's other fields where there is a lot of money to be spent. So pharmaceutical industry, the oil mining industry, you know, wherever there's big money to be made, they're going to be producing science papers, and they got lots of money to spend. That is going to make it sort of difficult for people who are trying to sort of be skeptical and study those papers to be able to push back against it. Astrophysics is kind of none of that, right? That there are really only a few thousand working astronomers on the planet, in the universe, but on the planet, maybe 10,000 at most, but I think it's more like in the, 5-ish thousand people are working astronomers in this field. They work at space agencies, they work at universities. There's not a lot of people. It's a very small community. And there's no money to be made, right? There's like no profits to be made when people discover a new black hole or discover a problem with the Hubble tension. And there's not really a lot of money that's being spent to destroy people's trust in black holes, or to destroy people's trust in the Big Bang. Now, you have obviously, various people, there are religions who have problems with the Big Bang. There are various conspiracy theorists who talk about various stuff related to space and astronomy, but it is very ad hoc. And so I think largely, and the kinds of observations, there's very pristine scientific instruments that can be done to make the observations. So it's very repeatable. And, I could look through my telescope, I can see a planet. You can look through your telescope, you can also see the planet. We can agree that planet is there. We have done independent observations. So astronomy works very well in that kind of field as well. So I think, there are always problems in various sciences, and there are bad actors in every field, including astronomy. But I would say, just like my observation, I don't spend a lot of time being deeply skeptical of the work that the astronomers are doing, and I'm looking for the angle, and I'm trying to, I don't have the need to do a lot of deep investigative work that you might have to do as a political reporter, or as a reporter working in another beat, because like in general, it's just kind of like you get what you see. Right? The scientists are making discovery. They're upfront about what they found. You can ask them questions about it. Nobody's really trying to hide anything. So it's a relatively straightforward field as a scientist, as a journalist. And I think as the scientists working together. Now, there are a ton of problems. There's the problems with the journals. There's a problem with peer review. There's the problem of tenure, lack of funding, mistreatment of grad students, all kinds of problems. But I think all human endeavor will have problems, and as a field of science goes, astronomy is pretty good. It's pretty fine. But people I'm sure would disagree because they live in it and they just experience the horrors every day. But I get to stand outside of it, sort of watch from the outside as the papers pop out. So here's an example. Was it Cheriastron? American archaeologists have abandoned Clovis first. Absolutely, but it took years after a proof was offered. Any comment? No, I mean, that's just like how science works. Someone finds a thing. They propose a theory that explains that thing. Other scientists examine that thing, and if the evidence lines up, then there will be a provisional acceptance of the evidence, and then other people will find evidence that is counter to that thing, and then there will be this evidence war as people are attempting to provide better and better proof for the perspective they're bringing to the case, for the hypothesis that they are attempting to disprove. And eventually, if some other concept has more evidence, then the scientific consensus flips over. That's how science works. That's how you know it's working, is that when scientific consensus gets overturned. That's a beautiful thing. You want to see that. You want to see scientific consensus get overturned because it means that the system is healthy. It's flushing out the toxins. Now, I don't know this specific thing. Archaeology is not my specialty, so I don't know what the controversy is, and I don't know how the back and forth went or any of that kind of stuff. But just like in general, if you told me that there's a bunch of scientists who used to believe in one thing and now the scientific consensus is a different thing, I'm like, yeah, that's how this works. That's science. Okay, we've reached the end of our episode. So thank you, everyone, for hanging out with me tonight on this Monday evening. Now, I cannot guarantee it, but you might see me again in a few hours. No guarantees, but depending on if it's clear sky right now, then I will try to do some more telescope observing. And if I do telescope observing and the system is stable, then I'll try to live stream it. So if I live stream it, I might be back later on tonight. But again, no guarantees. The code is battling me. All right. Thanks, everyone. And we will see you next week.